Okay, so welcome to this recording. I'm going to summarize what we did at the end of last class, and that was to talk about the hyperfine splitting in hydrogen. And this will set up the worksheet that I've asked you to do, and in the next video, we'll summarize the solutions to that worksheet. Okay, so what I have on the screen is our basic picture of the hydrogen atom before thinking about spin. We have the proton and the electron, and what we're going to be focusing on is the ground state of that system. And so before we include spin, there's a single ground state, which we call 100. And so that had the lowest energy, which is E1 equals minus 13.6 electron volts over 1 over n squared generally, but here we're talking about n equals 1, so it's minus 13.6 electron volts. But now we're wanting to take into account a very small but important effect, and that has to do with, number one, the fact that the electron has a spin. So the electron has spin half, and the proton also has a spin, which is also spin half. Okay. So that's the new thing, that the proton also has spin 1/2. And now the important thing is that the proton then, because it's a spinning charged object, it also has a magnetic moment. Okay, and so we can write that as mu for the proton. And again, it's proportional to the spin operator for the proton. So the magnetic moment points in the same direction as the spin. And it's the same formula as we had for the electron. So there's this factor G, which is a numerical factor. In the case of the electron, it was just 2. In the case of the proton, it is equal to about 5.59. So that's just how does this magnetic moment differ from the magnetic moment for just a classical spinning charged object. Okay. And so importantly for us, the proton also has then, because it has a magnetic moment, it's like a little magnet, and so it has a dipole field. So it has a dipole magnetic field. And so we can draw that. So that looks like this. Okay, so your standard kind of dipole field there. And so what's going to happen is that the electron, because it has a magnetic moment and acts like a little magnet, the electron will want to align with that proton magnetic field. Okay, so the electron spin, in order to lower its energy, it would want to align with this. Wants to align with this. And the interaction, or the term in the Hamiltonian that will take that into account, is the same one that we've talked about before. So that is just minus the magnetic moment operator for the electron dotted into the magnetic field of the proton. Okay, which I've drawn, but I haven't written. You can find the full expression for that magnetic field in Griffiths. Okay, so this is a sort of a tiny effect. We'll see it's a very, very small effect in terms of the energy compared to the ground state energy, minus 13.6 electron volts. But it is very important because it splits the ground state energy into multiple levels. Okay, and so how can that be? First of all, we started out saying there's this single ground state. So what we're talking about here is the fact that when you take into account the electron spin and the proton spin, instead of just a single ground state, we now have a space of ground states with 4 different basis elements. Okay, so we can write those as 1, 0, 0, and then I'll just use this spin notation where I write the electron spin and the proton spin. So up, up, 1, 0, 0, up, down, 1, 0, 0, down, up, and 1, 0, 0, down, down. So those are the 4 basis elements in our ground state, in our space of ground states before we add this interaction. And now we add the interaction, and what we want to know is what happens to the ground state energy. Does it get split? How much is the splitting? And so we're going to use degenerate perturbation theory in order to do that. And so the method is the same as usual. So what we want to say is for these states, so we have 4 states and we want to compute this 4x4 matrix of matrix elements for our perturbation, which is in this case this hyperfine splitting Hamiltonian. And so we can write those down. So let me call these, I'll define those to be G1, G2, G3, G4. And so what we want to calculate is the set of matrix elements GI, H hyperfine, GJ. Okay. And so like the spin orbit coupling, that hyperfine Hamiltonian, it turns out to have some spin parts and also some position parts. Okay. So remember, when we calculated the expectation value of the spin orbit coupling, we had to do some integrals to calculate, to take into account the position part, the 1 over r cubed that sat in the spin orbit coupling. And so similarly, there's some position integrals that we need to do involving the ground state wave function. So what I'm going to write is just now the spin part. When we do this calculation of this set of matrix elements, okay, after we take into account the position integrals, what's left is the following. So we get that this matrix of this 4x4 matrix of matrix elements for the hyperfine Hamiltonian turns out to be equal to some constant. Writing that out. A cubed, A is the Bohr radius. And then the important thing for us is that what you have left inside the matrix, oh sorry, these are G's. Okay, so those are our ground states, is this operator, which is the spin operator, the vector of spin operators for the electron dotted into the vector of spin operators for the proton. Okay, and so that's just like the spin orbit coupling, where one of those used to be the orbital angular momentum and one was the spin angular momentum. Now it's the proton angular momentum and the electron angular momentum. Okay, and so this sets up our worksheet. Basically what we want to do is think about this quantum system where you have 2 spin half parts, and we have a perturbation, which is some constant times the spin operator of the electron times the spin operator of the proton, and figure out, okay, what are the energies to first order in perturbation theory, and what are the corresponding eigenstates. Okay, and so we'll talk about that in the next video.